Here we go. Crash course. Ready? Circuits. Ohm's law. V equals IR. This stands for a voltage that drops over a component, and that voltage is traditionally given by, for a resistor, the current multiplied by the resistance of a resistor. Now, if you want to find the resistance of a resistor, it's a physical property of how you built that resistor there, and it's based off the following. It is built off of a resistivity, which is some constant depending on what you made it out of. Copper, aluminum, zinc, whatever, right? The flesh of the souls of humans. Whatever, right? We also know that this resistance goes up if we have a longer wire, so the length will increase the resistance, so it's in the numerator. And we also know that if we have a thick wire, that's THIC, if you got a thick wire here with a large cross-sectional area, that'll allow electrons to flow much more easily, so that'll be a capital A in the denominator. You need to be careful here. That A is the area, and for something like a circle for a cylinder, that is pi r squared. Okay, so careful about that one. If you double the radius, you have actually decreased the resistance by a factor of 4 because 2 squared is 4 and it's in the denominator. That sucker's coming down. Okay, so that's everything you need to know about resistivity. If you have an EMF, a battery, a 120 volt outlet, a power supply, whatever it is, if you have an EMF, you can have resistors in it. We can add these resistors in series, in which case it's just R1 plus R2, that's fine. Or these resistors could be in parallel, which if we're doing things in parallel, you want to be a little bit careful here, because when things are in parallel, you need to add them up in a slightly different way. If you're doing things in parallel for, let's call this resistor 3 and resistor 4 right here, if we want to break that in parallel, we know that the equivalent resistance of that is equal to, well, 1 over the equivalent resistance is 1 over, this is resistor 3 here, plus 1 over resistor 4, which means that after you divide, and then you add, you need to take the reciprocal of all of this. You need to do that sweet flip move, 1 over, in order to actually get the equivalent resistance. Okay? We also know that we start inside the most paralleled branch. So if we have something where it's like, here's a resistor, and then like more parallel nonsense like this, going way out, and then like down here there's like more resistors and stuff like that. We would actually want to start with this to make it 1 resistor, and then we'd bundle all of these together to make these 3 resistors 1, and then we'd bundle, so we do the pink first, and then we'd run all of that as orange, and then we'd run all of that as blue. So we work inward to outward. So that's just how we add resistors together. We are careful about that. We know that if we are going through resistors in series, we know that the current is the same for each of those, okay? Because there's only one line of current. But we do know that the voltage drops, as we draw them like this, could be different. And they could be different because while the current is the same here, each one could have its own independent resistance, which would cause their individual voltage drops across them to be different. So we don't exactly know if they will be the same or different. They can very well be different there. For these parallel setups, we know that as this current runs around the river bend, I'm current now. I don't know what that was. That was so weird. I just went Pocahontas on us. If this is the total current, or I1 here, we know this will be some I2, and then coming around this bend will be some I3. I2 and I3 don't have to be the same. At this junction, at this node point right here, that current splits like the 3 rivers. But what we can say is that from junction to junction, the voltage drop across these will be the same. So it doesn't matter if I had like an extra resistor right here, we'll call it like R5. Going from green dot to green dot will still give me the same voltage drop, and that's what we saw in Wild Bill. Wild Bill can be a bit of a headache because you don't give a lot of stuff there, but that's the idea, that's the rundown. Okay, and we talked about in class how there's some like clever ways that you could do ratios to solve this, or I just like working through it long ways because I know I'm going to get it right when I do that. If we talk about power, there's a few ways we can talk about it. Power we traditionally think of as being the brightness of something like a light bulb. And in general, we know power can be written as PIV, P equals IV. But we also know that, hey, look, Ohm's law is a thing here. And if I can write voltage as IR, that means I can sub this sucker in. And that means I could write this as I squared R. Hoo-hoo. I also know that if I kind of rewrite this differently and I solve for current instead, I know current is voltage over resistance. So that means I could rewrite this as voltage times voltage is voltage squared over resistance. All of these are power. Okay. What I like to do in problems when I'm trying to determine like what's going to be brighter, what's going to be dimmer, is I like to look at, if I'm comparing two light bulbs, I say, what do these light bulbs have in common? If they're in the same line together, well, they're going to have the same current, but are their resistances different? The one with the bigger resistance will have more power, it will be brighter. If these bulbs are in parallel, if it's like, oh no, you know, I've got one bulb over here and the other bulb over here, I can't use the currents because the currents, as we saw previously, have split around the river bend. Okay? But I don't care because I know that from here to here, the voltages are equal. So I can say, hey, look, these voltages are constant. I just want to know, I know the resistances, so I'll use this. Maybe you don't know the resistances, but you know the currents and the voltage drop, so you'd use this. So you just look, what do I have that's similar to both of these? What can I say? And then which one can I kind of pivot to? But that'll give us a power. And power is just a brightness. If you want an energy used, we say that power is a work or an energy divided by an amount of time. So you can say a power multiplied by a time equals an energy. So if you have something in watts, well, you can turn that into kilowatts by the metric prefix of kilo. And then if you take kilowatts and you multiply it by a time, like hours, you will have kilowatt hours, which is how your electric company bills you, because that is a true energy. Okay? And if I had something where it's like, you know, each kilowatt hour is 10 cents, I can say, well, you've got some number of kilowatt hours here, and it is, you know, 10 cents for 1 kilowatt hour. And then as Rush and Frazee and Dawson would say, train track fence post these away, and now I'm in money units. So there goes my paycheck again. What else we got? What else we got? And then the last big thing, well, not the last thing, but the big thing is Kirkoff loops. But just remember, if you are adding up capacitors, capacitors in parallel add like resistors in series. So the equivalent capacitance here would be 1 over C1 plus 1 over C2. It's also important to recognize that when capacitors are in series, they build up the same amount of charge on each of them. Okay, they build up the same amount of charge. When you have capacitors in parallel, each one can build up charge independently. So they're going to have different amounts of charge here. But this means that the equivalent capacitance is just equal to each one added together, because you can just store more charges. Okay. You know that, once again, because these are yay diffie Q for charging of capacitors. Oh, okay, yeah, don't want to do that. But that, yeah, that's what's going on. But you know they're gonna have the same voltage drop across them because voltages have to do that in parallel. These ones could have different voltage drops across them depending on the equation, because you know charge equals the capacitance times the voltage. If each one has different charge on them and different capacitances, the voltage could be all plethora of things, right? So just keep that in mind with capacitors. You're using a little bit of this, but really, are they same charges or are they different charges when you're doing that? And this is an important equation here, Q equals CV. And then last but not least, we have Kirkoff loops. The easiest Kirkoff loop is Ohm's law. So here's just a most basic EMF with a resistor. If we run around this, let's just pick a direction of the current. It doesn't matter. Let's just pick this way. This is our current. And if we pick the direction of the loop, it once again doesn't matter. Let's just pick this way. When I do this, going from negative to positive on my EMF will always be a positive epsilon, and then because I am going with the voltage, or with the current, excuse me, the current's coming down and my loop's going with it, I'm going to have a minus IR, and then when I come back home from where I started, that will equal 0. This is just Ohm's law because E equals IR, and we know this epsilon here, that's just a voltage, so there's Ohm's law for you. Mr. Botzer, I drew my loop the other way. I don't believe you. Okay, student, let's cover this. So I'm drawing my loop the other way. Well, what's going to happen? Well, let's just start here. Well, I'm going across the battery backwards, so that's minus epsilon. That's a bad epsilon. Okay, so I'm going across the battery backwards, negative epsilon, I'm losing voltage. I'm coming here, I'm going across the resistor against the current. So if I go against the current, that's going to give me plus IR, because I'm going from a low to a high potential, and this will equal 0. And now if I just dump this to the other side, I find that IR equals epsilon, which is just IR equals the voltage, which means that this is Ohm's law, and that's Ohm's law too. Oh, but Mr. Botzer, I also had the current backwards. Everything's going to change. Oh my goodness. Why are my students like this? Well, it's because they're learning. So let's say I run my current backwards because I was just like, I didn't know. Okay? Well, let's see what happens. I'm going to keep my loop in the same direction, but draw it in orange this time. And this time, what's going to happen is, because I'm starting here and going backwards across the EMF, I'm going to have a minus epsilon again. And then this time I'm going with the resistance, so it's going to be minus IR, and that is going to equal 0 for me. And what I'm going to see here is minus epsilon equals IR. Or I could say this. I can move the negative to the other side. And if I do that, you might be like, oh, Mr. Botzer, see, this one's different. This one's different. This isn't Ohm's law. There's an extra negative here. Okay? That's a mistake. You messed up. And yes, I did mess up. Because we know that conventional currents go from positive to negative. I know that this current I drew here was incorrect. So that's what that negative means. It means your current was backwards. So if you get a negative current, you drew it in the wrong direction. And that's totally fine. You know that. You're a great physicist. You got this. Okay? If you wanted to do more advanced Ohm's laws, or Kirkoff loops, excuse me, you could, because you're the best. This is the demo one we kind of did in our little video. I don't know, there's more resistors in various places here. But when you're doing this, you first need to set up a junction rule, right? Here's a junction where things kind of branch together. And you know there's 3 wires there, so there's going to be 3 currents. I've got I1, I've got I2, and I've got I3. And if you're looking at that, you're like, oh, ho, 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 Mr. Botzer, you can't do that. You're right. I can't have all the currents come into this junction. Because if all the currents come into the junction, that's like having all the trains come into the train station. How do they get out? If all the water only comes in, that doesn't matter. Like, how does the water get out? Like, water has to get out. So 1 or 2 of these currents have to flow outward. So let's just make I3 flow out. Doesn't matter which one you pick, because remember, as we saw at the previous Kirkoff loop, any decision you make here will solve itself out with linear algebra. Okay, as we use row reduced echelon form in order to set this up, or any other matrix solving equation that you feel like, because you're a highly intelligent student that's watching this in college and you're like, oh, I took a numerical computations class and I know all sorts of ways to do this. Watch me use my singular value decomposition method, whatever. You just know that some need to come in, some need to come out, doesn't matter how, boom, you did it. And then all you need to do is say, okay, I need to pick some loops. Doesn't matter the direction, so loop, and let's see, what color haven't I picked yet? Let's just go loop. That's it. With that, you've basically won. All you have to do is the following. You need to make a decision. For the junction rule, you're adding up all the currents and setting them equal to 0. Do you want currents going in to be positive and out to be negative? Sure. If you wanted to be backwards from that, ins or negatives, outs positive, nobody cares. It doesn't matter. The linear algebra solves itself. But let's call ins equaling positive and outs equaling negative. In this case, we're just going to have I1 plus I2. Remember, that's positive because it's implied. Minus I3 equals 0, because they always equal 0. If this is some EMF, and this is some R1, and this is... Here, let's just make all of our resistors nice values. Let's make them 1s. All of our resistors are 1 ohms. We'll just call this epsilon 1, eps 2, eps 3. For our left loop here, I'm going to pick a starting point behind the battery. I'm going to get a positive EMF out of that. That's nice. I'm going with the current across this resistor, so that's going to be minus I1, and then whatever resistive value is here. We said it was just 1 ohm for everything, okay, but that's really just, what is R here? What is this value of R? And as I keep going, I'm going down my loop, so I'm going with the current for I3 to go across this resistor, so minus I3 across this whatever ohm resistor, in this case it's 1. I'm going backwards across the battery, so I'm losing the second EMF, and then when I come out of this and come this way, I'm back into the I1 domain, because I1 actually goes all the way like that. So now I can just say, hey look, this is also minus I1 times that 1 ohm, and like everything, whenever we set up these Kirkoff loops, they are equal to 0. From here, we can do our left loop, same idea. We need to pick a place to start, so I don't know, let's pick here. I go up this EMF, so I'm gaining E2. I guess there's technically E1 up here. So I'm gaining E2, but this time I'm going this way, I'm going against this current. So since I'm going against the current, this is going to be plus I3 times whatever the resistance is. We said it's 1 ohm here. I'm going against the current up top, so this is going to be plus I2 times the 1 ohm resistor. I'm going backwards across the E3, so that's going to be minus E3, and then I'm going backwards against this current here because the I2 current comes all the way around. So this will be another plus I2 times 1. And then I'm back to where I started, so that equals 0. Woo! You did it. You set up all your Kirkoff loops. At this point in time, it's just a matter of setting this up to a more linear algebra standpoint and crushing numbers. We'll look at coefficients. The coefficients in front of all of these are either positive or negative 1. In this case, it's positive 1, and then negative 1. So 1, 1, negative 1. And then the augment of the matrix is whatever our EMF is, so that's going to be 0 here. If we look down here, we can combine terms for a few things. Note this is a negative 1, and this is a negative 1. So when I put those together, I'm going to get negative 2 for I1. So this is the I1 column, I2 column, I3 column, and then the EMF column. So for I1, I'm going to have negative 2. There's not an I2 here, so it's 0. And for I3, it's negative 1. I don't have numbers for it, but I'd have to take E1 minus E2, and that would be my EMF over here. So I don't know what number it is, but this would be E1 minus E2 or EPS2, whatever number that is, it would go there. And if I look at my third row here, do I have any I1s? Nope, so it's going to be 0. Do I have I2s? Yep, I've got 2 of them. I've got 1 and 1, so that adds the 2. They're both positive. And then for I3, I've got 1. And then here, it's going to be EPS2 minus EPS3. And I don't know what number that is, but if I did, there'd be a number there. And then, boom, you have just set up a wonderful matrix here. Technically, it is augmented. And we know that if we put this into the row-reduced echelon form in your calculator under whatever matrix you've put it in, it will kick you out a nice answer here, where your answer will be in the form of a identity vector or an identity matrix, so that the answer here, whatever number this number is I1, and whatever number this number will be I2, and whatever number this number will be I3. And remember, if those values are negative, that just means you picked backwards, and you'll just go back and flip it, and you'll call it a day. Okay? So, whew. That is that's the unit. That's the unit in a nutshell. Unit in a nutshell. Unit powers.